Hello everyone and welcome to the third webinar of the week, hosted by myself. Today's guest speaker, we have Drew Swartz, going to talk to us about camera-based systems. And Drew completed his Bachelor of Science in Animal Sciences at the University of Missouri, where he developed an interest in dairy production systems. He then went on to pursue a master's degree in animal science at the University of Minnesota under the guidance of Dr. Marcia Endres. Hopefully I've pronounced that correctly. His master's research focused on herd management practices in automatic milking systems, providing insights into how technology can shape daily operations on dairy farms. And in 2025, Drew earned his PhD from the University of Minnesota College of Veterinary Medicine, working with Dr. Gerard Kramer. His doctoral research centered on the use of autonomous camera-based systems to detect hoof lesions in dairy cattle, as well as exploring the perceived barriers that prevent producers and stakeholders from adopting automated technologies. So a bit similar to us here in the UK, really. This work combined technical innovation with social science inquiry, reflecting Drew's commitment to understanding both the tools and the people who use them. At the Utah State University, Drew's primary role is an extension with strong emphasis on producer-driven research. His vision is engaged directly with Utah's dairy producers to identify their needs, concerns, and priorities, with minors in data science and epidemiology and training in social science methodologies. Drew is uniquely equipped to collaborate with a wide range of stakeholders, including hoof trimmers, nutritionists, veterinarians, and producers, to co-develop solutions that are both practical and evidence-based. He is particularly passionate about helping producers make informed decisions about technology adoption by sharing real-world experiences, outcomes from other farms. His goal is to create feedback loop between research and practice, where producers' input shapes research questions and research findings directly from management strategies. So there's a fair background there, Drew. And well done on your doctorate, by the way. I'm going to now hand the floor over to yourself, and I'm going to mute myself and turn the camera off.
Perfect. I will share my screen. Are you all able to see the slideshow?
Yes, we can see it, Drew.
Okay, perfect. Okay, so hi everybody. Sorry, I'm trying to have this set up so that I can also see the audience at the same time.
Would you like,
okay, so go ahead.
Drew, would you like people to turn their cameras on or off?
No, so I think, so I can't, when I share my screens, I can't see the Teams meeting as well. So is it fine? I just take questions at the end?
Yep, sure.
Perfect. All right. Okay. Okay, hi everybody. So today I'm going to be presenting on some of the work that I did in my PhD at the University of Minnesota, but then some of the continued research that I'm working on as I start my role here at Utah State University. So as a brief background, so I did my PhD at the University of Minnesota, and all of the research projects and topics today that I'm going to be talking about is going to be about my work that occurred during my studies at the University of Minnesota. So again, my PhD was in veterinary medicine, and I was guided by Gerard Kramer. So here my PhD really focused in on lameness technology, and I had minors in data science and social sciences. So the way that I split my presentation up is into 3 different sections. So the first section is going to be talking about the background of lameness and hoof lesions, then starting talking about what my goals of the research was throughout my PhD and what we actually found out. And then I have it split up with the conclusions at the end. So the first thing that I wanted to do is define or talk about how we're going to define lameness, since depending on who you talk to and different producers that you speak with, everybody seems to have a differing definition of lameness. So the way that we want to define it here is that lameness is characterized by alterations in normal locomotion and postures, and it's often a result of pain. So when we think about a cow with impaired locomotion or a lame cow, we'd see this cow here, where she has an arched back when she's walking, she's not tracking up properly, she's bobbing her head, and she's not putting weight on the affected limb.
Drew, sorry to interrupt.
Yeah.
Your screens aren't moving on. Oh, no, they have. Yeah, they've just come on now. So it seems to be a little delay in when they change.
Sure, let me try to see if I can fix that. Sorry about that.
That's all right.
Let me know if this is better. Can you see the cow walking?
Yeah, that's much better. Thank you.
Okay. Yep. Okay. So using this definition of lameness, when we zoom out and look across the world, we see that lameness is prevalent across the world. And it seems to be an issue not just for North America, where I'm located in, but everywhere else as well. So when we go to start understanding lameness, it's important to remember that lameness itself is a result of pain. So it's not necessarily a disease or a disorder, but it is a clinical sign of impaired locomotion. So when we look at the multiple causes of lameness, we see that there's multiple factors such as arthritis, muscular ruptures, neurologic diseases, trauma, and hoof lesions. And I specifically put an asterisk next to hoof lesions because studies show that 70 to 90% of lameness events involve some type of hoof lesion. So when we look at why this is important and what the negative impacts of lameness are, what we see is that lameness has a negative effect on animal welfare, right? So lameness is a clinical sign of impaired locomotion, and it's often a result of pain. Then we see lameness also affects profitability negatively, as we see decreases in milk yield and decreases in reproductive performance. And we also see that lameness is an obstacle for greenhouse gas reduction and environmental sustainability, as the lame cows are typically culled sooner than non-lame cows, resulting in more excess production of young stock. So when we want to start looking at how we can actually detect lameness or detect hoof lesions, the main method or the current referent method that is currently used and accepted is the visual locomotion scoring. So this is a practice where you look at a cow and you evaluate their gait, and it's conducted on a bunch of different scales. So we've seen scales as 0 and 1, where a cow's not lame or a cow is lame, all the way out from 0 to 100. So regardless of the scale, there's typically 2 methods of using routine surveillance or using these visual locomotion scorings. So the first one is going to be passive surveillance, which is where workers are going to be identifying lame cows while they're doing other tasks. So here we can see somebody operating a skid steer, and they happen to look over and see a lame cow. But the problem with passive surveillance is that you are doing a different task, so you might not be able to identify the cow that was lame. Additionally, even if you do identify a cow that is lame, you could still have the opportunity to miss other cows that are lame. So the alternative to passive surveillance would be routine surveillance. This is where you have a person and time dedicated to locomotion scoring the herd. So the benefits of routine surveillance is that when you see a cow that is lame, you can have earlier detection. And when you detect the cow earlier, you can receive prompt treatment for the cow and get this cow treated or sent to the hoof trimmer or provide a therapeutic intervention to help alleviate the cow's lameness. However, problems that we see with visual locomotion scoring is that these tasks require both time and labor. And in the United States, there's a lot of labor shortages on dairy farms here. So if someone calls in sick or they just don't have somebody equipped to do the locomotion scoring, it's likely that it's not going to be a top priority task. The next issue we see is that we have this idea of chronic cows or chronically lame cows. So for example, here in January, we could be doing locomotion scoring and we can identify a cow that's lame, and it turns out that she does have a hoof lesion. So we can send her to the hoof trimmer and get her treated, which is the goal. However, we can be locomotion scoring the herd again in April, and we see that this cow is still lame, and we can send her to the hoof trimmer, but she might not have a lesion, and this would be the impact of having chronically lame cows, where cows are lame, but there's not necessarily a treatment or a hoof lesion that can be treated to improve their lameness. So then we run into the issue with visual locomotion scoring with lesion variability. So across the top here, I have different hoof lesions. So we have digital dermatitis, sole ulcers, and white line disease. And research shows that each of the different types of hoof lesions can have differing impacts on locomotion. So maybe there's a cow with a digital dermatitis hoof lesion and she might not be lame. Meanwhile, there's a cow with white line disease that is severely lame. And even within each of these classes of hoof lesions, depending on the lesion severity, we can also expect to see differing locomotions or differing resulting locomotions of the severity of the hoof lesion. So when we look at the use of visual locomotion scoring, there really isn't a surprise that there is poor sensitivity when we use visual locomotion scoring to detect cows with hoof lesions. So diving into some of the work that we did with my PhD. So one of the first things that we wanted to do was work with a different technology out there. So the technology that we worked with was the CattleEye technology, which is a computer vision type of program, which can provide locomotion and body condition scores for dairy cattle. So the way that this technology works is that it's installed above the return alley, leaving the milking parlor back to the pen. And it's installed above the ground, so it's looking down on the backs of the cow. So ideally, when a cow is done milking, she'll exit the milking parlor. And then on her way back to the pen, she'll walk under the camera. And as she's walking under the camera, is going to take a video of the cow and then run through its algorithm and provide us a mobility score or a locomotion score ranging from 0 to 100, where 0 would be a sound cow and 100 would be a severely lame cow. So, and the technology also produces body condition scores ranging from 1 to 5, where 1 is extremely thin and 5 is overly conditioned. And this also ranges from 0.25 increments So when we first started this project, we wanted to do a literature review and understand what other researchers have already done when it comes to using machine learning and hoof lesions and lameness type of research. So when we did our literature review, what we saw in the research is that there's multiple technologies being used right now trying to identify lame cows or cows that have hoof lesions. And what we've seen, some of the technologies that we came across are pressure platforms, some other computer vision-based methods, and accelerometers. However, in our mind, one of the things about all the different technologies, one of the problems with a lot of different technologies is that they give you a lot of data, but data alone does not give you actionable insights. However, one tool that can be used that can use a lot of data to assist in turning data into actions is the idea of machine learning. So this led us into being interested in looking at how there's different machine learning or different studies that are using machine learning to identify cows that have hoof lesions or lameness. So what we said was, let's do a review and see what topics are currently out there regarding machine learning, and specifically in the fields of lameness and hoof lesions. So with lameness and hoof lesions in mind, we actually came across 20 different studies that had an outcome being hoof lesions or being lameness. So for this plot here on the y-axis here is we have what their outcome they were using in the machine learning studies. And then on the x-axis, we have the percentage of studies using that outcome. So what we saw is that the majority of studies were looking at being able to classify or use machine learning to classify cows according to locomotion scores. And then we saw less studies actually using hoof lesions as the outcome. And then we saw only 2 studies that actually looked at you classifying both cows according to their locomotion score and according to their hoof lesions. So interesting within these studies, we also wanted to see how they performed their external validation, or how they actually evaluated the performance of their machine learning models that they created. So again, on the y-axis here is we have training and testing, which means that the studies or the authors of the papers that were published, they took their data set and split it into a testing set or a training set, and they trained the model on that, and then they made predictions on the remaining testing set. Then we have which was the most commonly used method, and then we have cross-validation. And then coming at the bottom, there was only 1 study that actually did cross-validation and a training and testing set. What was really interesting in this paper, or in this literature review, was that we only found 2 studies that actually performed an external validation, meaning that they applied their machine learning models in the real world and got results. So the reason that external validation is important is just because it worked on the original data set and in like a controlled fashion, we have no idea how it's actually going to perform when we apply it across different farms and try to see how it works in, say, the real world outside of that training data. So as a brief recap of this section, lameness and hoof lesions are a challenge across the world for the global dairy industry. The current detection methods are flawed for identifying cows that have hoof lesions and cows that are lame. However, technology and machine learning seems to offer promise for bridging this gap. So one of the first things that we wanted to do was evaluate how the CattleEye system technology works and see how it performs in the real world setting. So the first study that we did and was published was we wanted to see if this system can actually identify the cow that it's supposed to be looking at. So the way that the CattleEye technology identifies the cows are that each cow is equipped with an RFID collar, and this connects to the technology to let the cows know that they're there. Additionally, the technology also performs a recognition of the back of the cows, as seen in the picture, similar to a Face ID, to pair the RFID collar to the physical cow. So briefly, what we did is we went in and found cows that were relatively fresh or early in lactation or new to the barn, and then we painted the backs of these cows. So this consisted of us doing this experiment on 2 different sites, and you can see the different number and letter combinations that we painted. So then at the end of each day, we logged onto the CattleEye system that the user would have, and then we watched daily to see if the cow ID that we marked would pop up in the video presented there, and we could be able to record the cows or see our painting marks on the cows. So overall, we enrolled 103 cows, and across the 7 days that we observed, not all of the cows were identified. So we had 16 cows not identified throughout our 7-day period, but we only did have 1 cow that was misidentified once it was accurately identified. So what we took away from here is that the technology can reliably identify each specific cow, but it's going to take longer than 7 days for some cows. And one of the big limitations of this study is that we stopped it right at 7 days, and we should have followed it until all the cows were identified. So the next area that we wanted to see was, we know that the CattleEye technology does produce locomotion scores, and we wanted to see how this data actually related to the hoof trimming data. So this is also another paper that's published in the Journal of Dairy Science in collaboration with the Council on Dairy Cattle Breeding. So for this study, we took 5 years of hoof trimming data from 3 different farms. And if in the hoof trimming data, the cow just had a routine trim with no hoof lesion recorded, this event was then recorded as a trim event. However, if the cow had a hoof lesion where a therapeutic intervention was involved, this was recorded as a lesion event. So from here, we then paired the locomotion scores to the hoof trimming events, where we took the hoof trimming event as day 0, and then we created weekly locomotion scores leading up to that hoof trimming event. So here would be the average locomotion score 1 week before the hoof trimming event, 2 weeks before, 3 weeks before, and 4 weeks before. So on this plot here on the y-axis, we have the locomotion score. And then on the x-axis here, we have the weeks from hoof trimming, where it's 4 weeks out, 3 weeks out, 2 weeks out, and 1 week out. So when we look more at the black line, at 4 weeks out, we see that the median score across the 4 weeks stayed relatively consistent at the population level, where we saw a slight increase from 39 to 40. And then when we look at the cows that had hoof lesions, at 4 weeks out from the hoof trimming event, we already see that the median distribution is higher than the trim category. And then as we look at the scores for the lesion groups across the 4 weeks, we see that there's a higher increase of about 6 units from 4 weeks out. Meanwhile, the trim group only had an increase of 1. However, there's challenges when we use this technology, specifically if we're going to try to use a single threshold approach. So if we use one of the current recommendations of 50, what we see is that any trim cow above 50 is going to be a false positive, and any lesion cow below the 50 is going to be a false negative. So what we see here using a single threshold approach is that there's going to be difficulty using this technology at an individual level, even though we somewhat see population level differences across between the two groups. So from here, we actually wanted to see how producers view lameness and how they view different technologies. So we then created a survey to figure this information out. So we created a survey, and we had different dairy industry organizations here in the US we our survey across their mailing list. And our goal here was to get our surveys to those interested, we were interested in getting our surveys to those that were in managerial positions. So one of the first questions that we asked the producers or the respondents of the survey is, what items need immediately improved on your dairy farm? So on the y-axis here, we have the count of being selected. And then the first item that we see being the most important, or needing to be the most immediately improved, is milk production. And then after milk production, we had a 3-way tie with free time, lameness, and mastitis, kind of indicating that milk production is clearly the top concern for dairy producers, but coming after that, we see lameness is in the middle for being an item that is needing to be improved, as half the producers evaluated it as needing that. So then we wanted to zoom out a little bit and just see how dairy producers, so we wanted to ask dairy producers what their awareness are of different animal health detecting technologies. So on the y-axis here would be lameness detecting technologies, transition disorder detecting technologies, mastitis, and sick calf detecting technologies. And on the x-axis here is we have our scale. So over here on the right side of the graph, where the proportion or the percentage is going to be, this is going to be the percentage of participants that are moderately or fully aware of a technology. And on the left side is going to be participants that have no clue or are slightly aware of the technology. So we see that producers are aware of technologies for lameness, transition disorders, and mastitis detecting technology. So that producers are aware. However, when we then surveyed producers, specifically asking if they do use or if they don't use a lameness detecting technology, they were split down the middle, where only half of the respondents in our survey were actually using a lameness detecting technology. So we decided to investigate what the users perceive of this technology. So on the y-axis are different characteristics of the technology. So whether or not the technology is accurate, if it's reliable, if it saves time, or if it saves money. And on the x-axis here is the scale again. And on the right side, this percentage here is going to be those that somewhat agree or strongly agree. So across all users, the majority result is that the results are favorable for lameness detecting technology, as it's accurate, reliable, and most of the producers perceives that it saves time and saves money. So if we know that half of the users report time and money savings, and that respondents are aware of lameness technology, what is the key factor that makes only half of the respondents using a dairy or a lameness detecting technology? So then we decided to survey those that aren't using the lameness technology. And on the left side of the plot here are the different barriers preventing these respondents from actually implementing the dairy technology. So when we looked at the reasons that were above 50%, we see that the top two of the top reasons involve a financial benefit, where the greatest barrier to implementing a lameness detecting technology is the high startup costs, and then the other is going to be that it costs more than benefits. So when we look to the literature, we do see that producers need to see a financial benefit when it comes to implementing or making management changes, specifically with monitoring technologies. So one of the ways that we're going to store in our head of ways that we can show producers a benefit of a lameness detecting technology is through the idea of trimming cows without hoof lesions can lead to a reduced short-term milk yield in some herds. And the second top reason was that producers prefer identifying lame cows themselves, or they have the perception that they can. However, when we turn to literature, we do see that producers' perceptions of their ability to identify lame cows do slow adoption. So specifically in a paper cited here is that producers' confidence in visual detection methods slow adoption, but when you educate them on lameness prevalence and the cost of lameness, they have an increased favorability towards automated lameness detection methods. So when we surveyed the tech users or the respondents in our surveys that were using any of the technologies, we wanted to know how often they had false positives or how often they had false negatives. So again, the x-axis down here, or the legend at the bottom, for the left side here, we have the percentage of respondents saying never or rarely. And on the right side, we have the percentage of respondents that say they have false, or that they have the performance on the left often or most often. So we see that respondents are having false positives more than false negatives. And this is important to note because farmers' perception of a system is closely linked to its positive predictive value, especially when we see that false positive alerts can reduce the technology's usefulness, since it's going to increase labor and time demands for assessing healthy animals. So we wanted to take it one step farther and see what respondents were interested in when it came to implementing technologies. So on the left side here, we asked producers if they'd be more interested in reducing labor or if they'd be more interested in having earlier detection. So what we saw here with the two green boxes here being very interested and being somewhat interested, that our respondents to the survey were more interested in a technology or implementing a technology if it could reduce labor versus having earlier detection. Which makes sense because we've seen in other studies that farmers do prefer technologies that enhance automation and reduce labor demands over decision aiding tools. So with this in mind, with the previous work that we did and the survey work, we wanted to see if we could work with the CattleEye technology to continue making improvements. So it should be noted that our lab in Minnesota is not the only group working with the CattleEye system. We also have work coming from the University of Liverpool as well, where they made recommendations as well for this technology. So the study one is actually the study that actually suggested the 50 threshold, which was if it's 50 or greater, that cow would be lame or have a hoof lesion, and if it's 50 or less, it wouldn't. However, study two actually developed on these metrics, and they had day 0 as being the day from hoof trimming, and then they took 30 days of locomotion scores prior to the hoof trimming event, and they developed 4 different monthly metrics. So they created a monthly average, a monthly maximum, a monthly minimum, and a monthly percent above 50. However, there was one problem when we looked at these studies, or one thing that needed to be more clarified, is that though they were evaluated on the existing farms that they were created on and tested on, they might not perform well on other farms, which is that idea of external validation that we referred to earlier in the beginning, talking about the literature review. So one of the first things that we wanted to do was actually evaluate these recommendations through an external validation, where we took the thresholds and we applied them to an independent data set. So the study design that I'm going to talk about now is similar to the study design that I'm going to talk about in the next section as well, because it's coming from the same project. So for this study design, we recruited about 500 Holstein cows from 2 dairy farms. And each cow, and for cows to be enrolled into the study, they all underwent a sliver trim. So we just removed a sliver of hoof from their horn, and we applied hoof testers as well, looking for a withdrawal reflex. So cows could only be enrolled if they didn't have hoof lesions or a typically treated hoof lesion, which I'll talk about next. And then we followed these cows for about 100 to 120 days later, and we performed the same evaluation, except this time we gave them more of a routine trim. So depending on their hoof status at the follow-up period, we then classified the cows as the typically being treated group. So the way that we thought about making typically treated cows, or making this group, are those that require a therapeutic block or topical solution for treatment. So these included cows with an M2 stage of digital dermatitis, cows with sole ulcers, cows with a toe lesion, and cows with a white line disease. So then for our typically not treated cows are going to be the cows that aren't falling into the typically treated group. So they don't require more than a routine trim for management. So these are cows that would have a corkscrew claw, cows that had a heel erosion, hemorrhages, or they did not have a hoof lesion, but they had a pain, or they had a withdrawal reflex when we applied the hoof testers, which we indicated as being pain. So the results from here is, the way that we're going to interpret this graph is on the y-axis here is we have each of the different thresholds, followed by the point estimate or the accuracy estimate, which is also denoted as the circle. And then we have the 95% confidence intervals, which are going to be the lines that extend out. So what we saw here is that all the accuracies were relatively high. So most of them were above 65. However, in my opinion, accuracy does not tell the whole story when it comes to making classifications. So I'm going to show a bunch of different graphs that are similar to this, but I'm going to explain this one so that we can relatively cruise through the other ones as well. So on the y-axis here is we have the metric that they use. So this would be the 50 bin is the 7-week average prior to the locomotion or prior to the hoof trimming event. And then the dashed line going across the middle here is the threshold that was recommended for this or higher would be a cow that would have a hoof lesion, and anything below would be a cow that doesn't have a hoof lesion. So when we look above the line. So we have triangles above, meaning that these cows would be a positive prediction. However, when we really look deeper into it and we look at the blue, we see that there's more amount of blue triangles, which is going to be the true positives, compared to the orange upside down triangles, which are going to be false positives. So what we see using this 50 bin threshold is that the positive predictive value was only about 25%, meaning that 25% of the positive predictions were correct and 75% of the positive predictions were incorrect. And when we look below the 50 bin threshold and we start looking at the squares, the green squares and the orange diamonds, we see that there's a lot more green squares compared to the orange diamonds. And these would be our negative predictions, saying that anything below this threshold is a cow that would not have a hoof lesion. And we saw that 90% of the negative predictions were accurate or were correct. So when we go to look at the other metrics as well, we see a common trend of having a more poor positive predictive score or a lower positive predictive value. So for example, for the monthly average, we see a similar trend of having, and when we look at the positive predictions, we see a lot more false positives than we do having true positives. And this goes across the monthly maximum metric, the monthly minimum metric, and then the monthly percent above 50. And then the highest score here was actually the monthly average, where its highest positive predictive value was 23.7%. So with this in mind, that all of these different threshold-based approaches yielded a low positive predictive value, our idea was, can we somehow work with a machine learning algorithm to improve this low positive predictive value? So this led to the final chapter of my PhD, which was looking at seeing if we can develop and tune multiple classification models for hoof lesion detection. So coming from our survey and previous literature, we assumed that producers wanted a high positive predictive value. So for this, we tuned our model using an F0.5 score. This basically just means that we prioritize positive predictive value, but we also wanted to have credit for identifying a lot of the cows that had hoof lesions. We also identified that we wanted to reduce labor, so we wanted to use data to generate our hoof trimming list so that producers will not spend time creating hoof trimming lists or having to go through all the data themselves. And then we know that dairy producers, when they want to implement a technology, that they want to see a return on investment. So here we wanted to make sure that we're pairing it with the positive predictive value, that we're only identifying cows for hoof trimming that had hoof lesions. So we actually evaluated a lot of different machine learning model data sets or feature sets. So we included the CattleEye data, which included locomotion and body condition scores. We included milk production, changes in milk production, different levels of other cow demographics. And it actually turned out that we had the best performance when we actually only used the locomotion scores and the body condition scores from the CattleEye software. So for our project, when we wanted to look at our group or our incidence of the positive group or the typically treated group, what we saw is that we actually had a lower disease incidence for the hoof lesions that we were looking to identify. So on the y-axis here is we have the number of cows. And then for each of the bar graph sets, we have overall site 1, site 2. And then on the x-axis, we have typically treated and typically not treated. And across both the sites and even at the overall level, we see that we did have a lower incidence of the typically treated. And what we do know when it comes to making machine learning models or trying to do standardized testing, that the lower the disease prevalence, it typically decreases the positive predictive value. So we were already going to be struggling from the start with trying to make a machine learning algorithm that had a higher positive predictive value. So on the left axis or on the y-axis here, we have the performance metrics being accuracy, sensitivity, specificity, positive predictive value, and negative predictive value. And then on the x-axis here is we have the model that we used that was end up being performing the best, which was random forest, along with its training performance metrics. So when we trained our model, what we saw is that we had 100% performance across the board, which this is good to see, but then we run into the fear of wondering if we actually overgeneralize or overly generalize our model so that it's only going to be good on our training set. However, we then applied it to a different testing set that the data hasn't seen, and we did see a slight decrease in performance. Specifically, well, we saw a decrease in performance across all the metrics, but sensitivity and positive predictive value had the greatest decrease. So it looks as if this machine learning or random forest model that we made was going to be promising. However, we didn't stop there, because everything I said earlier would be about external validation would still be true about this. So we wanted to know if our machine learning model would actually perform well. So we decided to retest it on the same population, and we really just wanted to evaluate the positive predictive value. And this was a preliminary step, doing it on the same operation and just evaluating positive predictive value before spending a lot more resources on this idea that our machine learning model works. So we then moved on to then externally validate our machine learning algorithm. So the way that we evaluated the live performance was that we were going to be the ones that created the hoof trimming list using our machine learning algorithm. So we created a hoof trimming list for the positive predictions, and the day before the on-site hoof trimmer came, we uploaded the data into our pipeline and we made hoof trimming list. However, to reduce bias and keep us blinded and have the hoof trimmer blinded, the University of Minnesota and our research team, we stayed out of the hoof evaluation, and we let the on-farm or the hoof trimmer that the farm uses perform the hoof trimming evaluations. So it's also important to note that the hoof trimmer performs routine trims as well. So they were still blinded whether or not we selected the cow for them to be trimmed as part of a therapeutic, as being part of our group, or if they were just there for a routine trim. So this then leads to, how did our machine learning model perform live? So on the y-axis here, we have two different groups of being any outcome, meaning that the hoof trimmer made any recording about the cows that we wrote. And then we have the typically treated group, which are the cows that we were specifically looking for. So for here, we have our random forest model, and we had 58 cows, and our positive predictive performance decreased significantly from our testing set, where it dropped down to about 29% for any outcome. And then for our original outcomes of interest, we only had a positive predictive value of 15.5%. So what we saw here is that we had a poor predictive performance, even with the machine learning algorithm that we made. But before we threw it away, we wanted to actually see, thinking back to how the farm currently identifies lame cows, how did our machine learning model compare to passive surveillance, which the farm currently uses themselves? So on the y-axis here, we then grouped the cows that were similar, sorry about that. So for the y-axis here is we had our random forest model and our positive predictive value, and we had 32.4%. But when we looked at the farm doing their passive surveillance, they did identify fewer cows, but of the cows that they identified, they had a 75% positive predictive value, meaning 75% of the cows that the farm staff identified were truly that had a hoof lesion at the outcome. So showing here that the passive surveillance method that the farm currently used does have a higher positive predictive value. But when we actually looked at the cows that were being identified, on the left here is we have the 16 cows that our machine learning model identified, and we identified 16 cows that passive surveillance didn't, and passive surveillance identified 19 cows that our machine learning algorithm did not, And both the machine learning model, our random forest, and passive surveillance had an overlap of 8 cows. So this leads us to think, is it possible that the passive surveillance is identifying cows that are more severely lame, and our random forest might be identifying some cows earlier, prior to them becoming severely lame? So since we're identifying different subsets of cows, and maybe our random forest method is identifying them earlier, could these systems be complementary to each other, since both methods identified different cows? So in conclusion, if the big question is, does the technology work for lameness? I don't think it's a fair assessment to say whether or not the locomotion scores from the technology are realistic, or whether or not the technology, So specifically, since the technology was designed for producing locomotion scores and not detecting cows with hoof lesions, I think it's unfair to say whether or not the technology works, specifically as we did not evaluate how locomotion scores agreed. However, the idea for this technology from our perspective is at the farm level use, it would be used for hoof trimming. So though the producer could use the technology for identifying lame cows without hoof lesions, there is possible use for this technology for quality assurance programs or estimating lameness prevalence, and there's currently no study checking apparent prevalence compared to true prevalence yet. Then it comes down to, is there value in the ability for our algorithms to have a hoof lesion detection? So is there any value in our hoof lesion detection algorithm? So there's a potential benefit in the different subset. So we have the idea that there's going to be more cows being identified, but what we don't know is we don't know the trade-off between a true positive and a false positive being unknown. So when we look at different cost analysis of having lame cows and non-lame cows, and cows that have hoof lesions and cows that don't have hoof lesions, a lot of the financial estimates between the two groups are from those that have had hoof lesions and those that haven't, or those that were lame and those that aren't lame. We haven't really seen any of those looking at when a cow has a hoof lesion and is treated versus isn't treated, and seeing how the financial estimates vary between the both. And additionally, here in the Midwest, what we see is that a lot of farms already do routine trimming. So we would expect to see all the mid-lactation or all the cows at least twice a year. So we don't know the financial return of the technology compared to routine trimming, especially as we did not evaluate sensitivity or specificity. And in theory, the mid-lactation trim would have 100% sensitivity. So thank you for your time. I'll exit out of this, and thank you.
Thank you very much, Drew. Very interesting presentation. So we're going to open the floor to questions. So you can turn your cameras on and unmute yourself, or you can put your questions in the chat box and I'll read them out. So we don't appear. Oh, we've got Paul. Hello, Paul.
Hello, guys. Thank you, Drew. Very interesting talk. I'm sorry I missed the start. Just had one thought more than a question, really, which is because the positive and negative predictive value are dependent on the population that you're surveying, presumably if you had a much lamer population, then the positive predictive value of the technology or any method of locomotion scoring arguably would be better, presumably. I can think of 1 or 2 herds where you could put this in. Basically, every cow that it picked out would have a hoof lesion, which is probably more a reflection of the farm than the technology. But at that point, I just wondered, was it a fairly low? Would you say your study was conducted in a fairly low lameness prevalence population, or?
Yeah, so that's a fair point, and that's something that I tried to talk about a little bit in the presentation. And I would say that the farm that we actually conducted the research on had a higher lameness prevalence or higher hoof lesion prevalence than what we expected. Or yes, well, they had a higher prevalence. But what we did for the study is that we recruited cows that only had a max history of 1 hoof lesion before. So we took a subset of that population, and we probably recruited a lot of cows before the chronic lameness actually started. So we had a biased population of those that weren't affected yet, but that was also where we were trying to target our group. So I was thinking that if we can identify cows prior to being chronic, then maybe we can prevent them from being chronic. So
with
yes,
the most value to treating. Yeah, I get it. Cool.
So yeah, our prevalence was lower than, I would say, a general population, but that's how we focused in on trying to make it valuable.
Cool. Thank you.
George, do you have a question?
Yeah. Hi, Tim. Hi, Drew. Thanks for the presentation. Have a couple of questions, and if you don't mind, a couple of just clarifications and comments.
Sure.
Yeah. So, I mean, if we start with the clarification, the second study you mentioned that we published, like the larger population, like the CHCSB study, most of these farms in this study were not used for the algorithm development. So you could say that this was external validation.
Okay.
I think you said that, yeah. Just like that, just to clarify. And my first question is whether you think, I mean, I'm all about what you were saying about improving positive predictive values and sensitivity and specificities, but we could also argue that we don't have anything better at the moment. Like at least the work we did, the human scorers, well-trained vets were not achieving better sensitivities or specificities. There are other studies where the sensitivities are even worse. Maybe specificities are a bit better, I suppose. So it's whether you want to go for the positives or the negatives. So that's what's your thought on that. But I do agree with you that we can take approaches to improve this. The data we get from the technology make better use of it. But what do you think about the alternatives we have?
Yeah, I think that's one of the problems is that I don't think a lot of the alternatives are. I think lameness is one of those things that are still complicated, and when we look at alternatives, I don't think there is a single answer yet for something that's necessarily better yet. But I think just when we look at the data that I had, one of the things that I wish we knew is that if we could see how those passive surveillance that had the higher positive predictive value and identified more cows and treated less cows, whether or not those cows were severely lame or if they were relatively early, just so that we could kind of get a better understanding of seeing how, like, the timing difference between the two. But I might have worked around the question. Could you re-ask your question if I didn't answer it?
No, I think yeah, that's fine. And then, I mean, that's also like I know it's more about asking questions, but if you don't mind me just adding something
Sure.
on your question on whether like we have any evidence that this works on top of the routine foot trimming, which I still have. I agree with you. That's another big question. We do have the data from our randomized control trial, which is not published yet, but you probably have seen it at the conference last year. I think we presented it. You were there at ADSA, where our control group was still getting the routine trim, so early lactation and mid lactation, would still get the passive surveillance, as you describe it, from the farm. But us using CattleEye scores every week led to significant improvements in chronic lameness lesion prevalence at the end of the study. So, okay, that's just one farm, but I just wanted to add that as some evidence towards the fact that this could work on top of the routine trims. The big question I have now, and maybe on your thoughts on that, is whether you plan to do anything on this, is can we use it instead of the routine trims, or is it not there yet?
Yeah, I think whether or not we use it instead of routine trimming yet, I don't think that I'd currently make the recommendation that we stop doing routine trimming yet, just because I don't think all the data is necessarily there yet. I mean, I know there's a lot, or I know that I bank a lot of the negatives of trimming cows without hoof lesions on that one study showing the short-term milk yield, and then depending if there's an in-house trimmer or not. But I don't think that I'd make the recommendation yet of just using the locomotion scoring or just using the CattleEye data or my algorithm or anyone else's metrics to bypass routine trimming yet. But I don't know if you I don't know if you have differing thoughts on that, but that's
No,
kinda...
well, no, I don't, because I haven't done the research for this. Our randomized control trial, the cows were still getting routine treatments. So CattleEye was on top of that. It did help, so I can say that. But I wish I had a group that was only managed by CattleEye. But I don't do that, so I don't know. Yeah, I agree with you. Like, I don't recommend it at the moment. I still recommend routine trips, but I would be very interested to play with that at some point and see whether we could avoid some of the potential negative impact of this handling and stressing if they don't need it. But yeah, I agree with you 100% on this.
Yeah, I think we could identify the cows that need trimmed and get those trimmed, and yeah, absolutely, we can get away with trimming every cow. But until we can figure that part out, which I think is going to be the hardest part.
Yeah.
But thanks for the questions.
Okay, thank you. Could I ask the both of you, Drew and George, do you think going forward then, listening to what you were both saying, do you think we'd get away with not trimming certain cows, just using the CattleEye or using a locomotion score?
I think if we can, yeah.
No, go ahead. Sorry, yeah, you're the speaker today.
Yeah, no worries. I think if we can get to the point where we can identify cows that are either going to be coming into a hoof lesion or soon, or that have a hoof lesion, we get those cows treated, I think that'd be great. But I think we can get to a point where not every trial or not every cow necessarily needs to have a mid-lactation trim if they're already set up for success. So we can identify them before things start going bad and only treat those ones. I think it would be a lot more practical. But whether or not, however long it takes to get there is the big question, right? So I'm not going to say stop trimming. I'm not going to.
Yeah, no, good. Thank you. Does anyone else have any more questions for Drew? Okay, so once again, Drew, thank you very much for your presentation. It's much appreciated. And hopefully we'll catch up with you again at some point at a conference somewhere.
Yeah, perfect. Thank you. I appreciate it. Thanks for having me.
No, thank you. Thanks all.
Thank you.